So in this video, we're going to learn how to write and use equilibrium constant expressions. And so by the end, you'll know when to omit solids and liquids, and how to use the reaction quotient in order to predict the direction of the reaction, and also how changing the equation will change your K. So just to start off, what exactly is equilibrium, right? So at equilibrium, the forward and reverse reactions are going to be occurring at an equal rate. So when you have a reversible chemical reaction, it doesn't just go in one way and then stop. Instead, there are going to be a forward and a reverse reaction that are both occurring at the same time. And so eventually you're going to reach a balance, which is what we call the equilibrium. And it's at this equilibrium that the concentrations of our reactants and products do not change anymore. But this doesn't mean that the reaction has stopped. The reactions are still happening. It's just that, the forward reaction is occurring at the same rate as the reverse reaction. We're converting reactants to products at the same rate that we're converting those same products back to reactants. So because of that, we end up having a constant concentration. So it's what we like to call a dynamic equilibrium. And we call it dynamic because there's still a lot of movement happening, right? The reaction hasn't halted, it hasn't stopped, the rate is not zero, but rather we just have reached a point where now the forward reaction is going to be equal to the reverse reaction. So it's this point that we get the rate, the forward, we call it rate sub F. The forward rate is going to be equal to the reverse rate, sub R, if we want to write it this way. And so to keep in mind that the concentrations, again, then here are constant. So concentrations, we call it concentrations, become constant. And this is, again, not because the rate is equal to 0. The rate is not equal to 0. And another thing to keep in mind about our rate constant, which we denote with this capital K, is that it depends on temperature. Changing the temperature in which a reaction is taking place will end up changing this value of K. So now that we have an idea of what equilibrium is, let's look at the general form of this equilibrium constant. The general form of this equilibrium constant. And so the equilibrium constant, which I mentioned, right, we denote with this capital K, is the number that is going to be telling us how much product we have compared to reactant once we reach equilibrium. So at equilibrium, how much product do we have relative to how much reactant do we have? So the general rule here is going to be products over reactants. Products over reactants. And so that means that if we have, we have each of these products raised to the power of their coefficients in the balanced, each of these products and reactants, rather, raised to the power of their coefficients in the balanced chemical equation. So that's another important thing, is that you have an accurate or correctly balanced chemical equation. So if we have this generic form for a chemical equation, let's say we have, little a sub a plus little b sub b, and again, this is a reversible reaction, yields little c, big C. I think I've been saying sub C, but big A, big B, little c, big C, little d, big D. So if we have this generic form for a chemical reaction, well then the equilibrium constant in the the molarity form, I'll kind of distinguish what that is in a moment, but in the molarity form, then we call it K sub C, our equilibrium constant, is going to be, as I said, the concentration of our product C raised to the power of its coefficient, concentration of D raised to its coefficient, divided by the concentration of A and the concentration of B raised to their coefficients. So it's a very, nothing too complicated here. This is what the general formula is going to be. So in place of these, letters, in square brackets, we would effectively just be inserting then the respective concentrations of these products and reactants once we're at our state of equilibrium. So this is what we do when we are dealing with molarity, right? We use these square brackets because that's what we use to denote concentration. But in some cases, what if our products or our reactants are in a gaseous state? So if we're in a gaseous state, so we're using gas pressure, right, instead of molarity, then if you want to call this case a P for pressure, well then again the general form is going to be effectively the same. Instead, it's just that we won't be using these square brackets because we're no longer looking at concentration. So rather we can use these round brackets, and we use this big P in order to denote pressure, and we write it as a subscript, what coefficient or what we're looking at. So this is P sub C, referring to this product here, and that's going to be raised to the coefficient. So we have the exact same thing as we had previously. It's just here we're just dealing with pressures as opposed to concentrations. So this is what we're going to be looking at when we're dealing with pressures, and this is what we're looking at when we're dealing with molarities. So hopefully you took a note of this. Let's just clear this up for a moment to make some room for another, a few more important points to take note of here. So we talked about how we set up this general equilibrium constant, right, using this general equation or form of this expression. But some things to keep in mind is that when we are doing this, pure solids and pure liquids are going to be omitted. These are omitted. These are left out. So if we have a product or a reactant that is a solid or a liquid, in our balanced chemical equation there, that is not going to be included in our equilibrium expression. So that means that only are we going to have our aqueous, our reactants and products that are in an aqueous state and in a gaseous state. So only the aqueous and the gases are going to be included. And so this is a very important thing and a common source of error. So make sure that you are not including solids or liquids when you are writing your equilibrium constant expression. And so also what you may have noticed when we did this is how important those coefficients are. So you can see that if you change the values of those coefficients, you will drastically vary what the value of your constant, equilibrium constant, will be. And for that very reason, it's important that you have a correctly balanced chemical equation. So make sure that you are doing that correctly and that you are also minding the values that you are inserting into your expression. So make sure you're putting in the correct concentrations for your products and reactions, and you are using the correct coefficients. All right, so now that we've kind of got an idea of how we deal with these equilibrium constant expressions, let's move on to look at what a reaction quotient is. What is our reaction quotient? And this we denote with a capital Q. So what is our reaction quotient, and how does this reaction quotient compare to our equilibrium constant, our big capital K? So Q is going to be really the same form as K. It's just that you're plugging in the current concentrations or pressures for Q. So in K, the concentrations that you are plugging into that general form, right? The form that we saw here. If we were looking at our, our products over reactants, these concentrations that we are, inserting into this general form that we have here are going to be those that we have during or once we have reached equilibrium. So these are the concentrations or pressures at equilibrium. But for Q, we will be using the current concentrations. So that basically means, if you want to think of it kind of like a syllogism, well then all equilibrium constants are reaction quotients, but not all reaction quotients are equilibrium constants. If hopefully, that makes sense, you can kind of understand the relation here. And so because we are inserting the concentrations at some point in the development or the progression of a reaction before or after before we've reached equilibrium or at a state not at equilibrium, we can then use this Q, and comparing it to our K, we can figure out the direction or predict the direction in which a reaction will proceed or the reaction will shift. And that's because we know that for any given temperature, for a certain reaction, our K will always be the same. As the name would suggest, it is an equilibrium constant. At different temperatures, even if we're dealing with the same reactants and products, yes, the constant can vary, but at a given temperature, for a certain reaction, your equilibrium constant will always be the same. And because of this, we can use this to our advantage to then compare our reaction quotient with our K in order to predict the direction in which a reaction will proceed. And this is something that we can, it'll make more sense if we look at it right now. So let's look at the possible relationships that we can have between our Q and our K, and then kind of looking at each of them a bit closer. So let's say if we can have, obviously we can say that if our Q is less than K, we can have a point where our Q is equal to K, and we can also have a point where our Q is greater than K. So these are three possible scenarios that we can have. So looking at the first one, what happens if our Q is less than K? What direction will this reaction shift? Well, we're looking at this, and from this we can tell again that our Q, our reaction quotient, is lesser than the value of equilibrium. So in order to reach our equilibrium constant, this Q number would have to increase until it reaches K. So what is our Q and our K? We know this general form is going to be our products over our reactants. So if we want to increase this Q until it becomes K, how can we increase the value of this fraction? Well, how do we increase the value of any fraction? We can do so by increasing the value of the numerator and decreasing the value of the denominator. And lucky for us, these two go hand in hand if we're looking at this type of reversible chemical reaction. And that's because any reactants that become products, or any of our product, is happening because we're converting our reactants into products. So if we're increasing the amount of product, we are inherently decreasing the amount of reactant because it is the reactant that we are converting into product. And so in order for this reaction to reach equilibrium, we're going to shift forward. We're going to shift forward, producing more product, which is again going to decrease also the amount of reactant, and overall it's going to increase the value of this fraction. It's going to increase the value of this Q until it reaches the value of this K. So hopefully that makes sense. Next, what if our Q is equal to our K? Well, if our Q is equal to our K, that means that we are at equilibrium. This means that we have reached equilibrium. There is no shift that is going to be taking place. Again, this is a dynamic equilibrium, meaning our forward reaction and our reverse reactions are going to be happening. They're still occurring. It's not, the rate is not equal to 0. But these two values of our forward rate is going to be equal to our reverse rate. So there's really no shift that is occurring if our Q is equal to our K. Now, what about if our Q is greater than K? If Q is greater than K, well then, in order to reach equilibrium, this Q, this fraction, this products over reactants, must decrease. It must decrease in order to become K. So how can we decrease the value of a fraction? We can do so by increasing the value of the denominator. So we need to increase the value of the denominator. We do so by producing more products. So that means here you are going to reverse, you're just going to shift in the reverse direction. Here we're going to shift in the forward direction. Here there is no shift happening at all. So there's no shift at all. But here, when our Q is greater than K, in order to reach equilibrium, the reaction shifts in the reverse direction, producing more reactants. How are we producing more reactants? Again, we are taking the product that we have formed and converting it back to reactants by proceeding in the reverse direction of our reaction. So this is how we can, produce more reactants and inherently thus decrease the value of our Q until it equals the K, which is what we would have at equilibrium. So it's in this way that we can use the values of Q. We can use our reaction quotient and compare it to our equilibrium constant in order to predict the direction in which a reaction will then proceed. So hopefully that is making some sense. Again, if you ever forget which direction you will proceed, if you have a Q less than K or greater than K, you can always just remember this relation that we have products over reactants. So if we are trying to, again, reach a certain K value, if whether or not we have to, depending on whether we have to increase or decrease, we can then remember how can we increase or decrease the value of a fraction. And based on that, we can then figure out the direction that this reaction will then shift or proceed. All right, one last thing to keep in mind before we reach the end of this video is how we can change the equation of, or a chemical equation, and how that affects our K. So if we had our generic form for a chemical reaction as we had previously, something like this, if this is the forward reaction that has a constant equilibrium constant of K, well then if this is for the forward reaction, if we wanted to write the equilibrium constant or figure out the equilibrium constant for the reverse reaction, that is just going to be 1 over K. 1 over K. It's going to be the inverse. And that makes sense, right? Because we know that this K is simply our products over reactants. In this case, if we call this 1 and this 2, right? Our products over our reactants in this case is going to be 2 over 1. But if we were looking at our reverse reaction, if we were looking at a reaction where we were converting our products C and D into our reactants A and B, well, in that case, it would be looking we'd be looking at something more like this, right? This is what we'd be looking at. And in this case, these two are reversed. And so our products over reactants in the first case was 2 over 1. But now, because these two have swapped places, it has now become 1 over 2. These are 2. These are the inverse of one another. And so that's again why we can simply take our K value. If we have the K value for the forward reaction and we want to find the K for the reverse reaction or vice versa, we simply invert it. 1 over the K of the others. So hopefully that makes sense. Now, what about if we are, let's say, we are multiplying all of these coefficients, right, by some value n. This is NB, n times C, n times D, n times D. So if we multiplied everything by some value of n, in that case, we would effectively, how would that affect our K? Well, we can simply take the original K and raise it to that same value of n. And this would give you your new equilibrium constant. And now finally, what if we had two separate reactions? Let's say we had a reaction converting A plus B, and this gives you C, or rather, let's do it this way. Let's say we were taking A and this reaction converts A to C, and B in the separate reaction. This is the first reaction, this is the second reaction. The second reaction converts B to D. And now let's say we want to couple these together. We want to merge these together. This one has its own K, K sub 1. This one has its own K, K sub 2. Now let's say we mix these reactions together. So now we have A plus B gives us C plus D. Again, this is an oversimplification, but let's, just for example purposes, let's say we do this. Then how can we figure out the new K? The new K for this reaction where we have this additive effect going on, is simply going to be the first K multiplied by the second K. So this is going to be equal to this, the K value for our new reaction that we have formed by combining the first two. So these are a couple of these properties that we see with regards to manipulating our K, or equilibrium constant. And so we can see how changing the chemical reaction, that equation here, can affect our K value. So keeping these in mind, and try to use these to your advantage when you're seeing different problems where you're given an equation in one form or another. Save yourself time by simply using these tricks to your advantage. So anyway, that brings us to the end of this video. So you should by now have a decent a good understanding of what equilibrium is, and an idea of how we can set up our equilibrium expressions, and how we can compare our Q and our K and predict the direction that a reaction will proceed. So hopefully you've got some utility out of this video. If you did, please show your support by liking and subscribing. Leave in the comments any questions you may have, what you would like to see next, and I will see you in the next video.